We now solve an example of somewhat more complexity. So we have a mass M2 sitting on a horizontal surface, tied with a string through a pulley to M1 and released from rest, and well, it's going to fall down. This is going to be pulled to the left. Well, let's add some more things to it. Let's say that there's a force F that's pulling it this way, in addition to the weight which is pulling it the other way, and we do have friction. So we have friction, and well, this is going to be M2G. So, and this is going to be the normal force, and this is going to be M1G, and there's going to be a tension pulling upwards, which is T1, and this is being pulled to the left with a tension that's T2. So we've seen such problems before. So if the pulley is massless and frictionless, okay, massless and frictionless, then T1 equals T2. But if the pulley has a mass, which means a moment of inertia, not zero, and being massless means the moment of inertia is zero. In that case, T1 is not equal to T2, and so we do need to write it as T1 and T2. So let's say the mass of M1 is M1, and mass of M2 is M2, and mass of the pulley is M3, and the radius of the pulley is R. And now when we release it, we'll write the equation and see what happened, and we'll add some numbers. So by conservation of energy, we would have the delta K, the gain in kinetic energy, would be plus the gain or loss in gravitational potential energy, there's no spring here, equals the work done, which is F dot D, minus the friction work, which is Fd, and we take the absolute value. Now the change in kinetic energy will be the delta K of object 1 plus delta K of object 2 plus the delta K of object 3, which is the pulley. Now as the pulley starts spinning, it will gain or lose some rotational kinetic energy, and that equals, we have the delta UG, so plus the delta UG for 1, that's the loss of potential energy for number 1, or the gain if it's going up, plus the delta UG for 2, any change in potential energy in number 2, which in this case is 0, equals F dot D minus Fd. So this would be a sort of a general equation. This would be a linear kinetic energy, this would be linear, and this would be a rotational for this one. Now if we write this a little bit in more detail, we would say the delta K1 is going to be half M1 V1 final square. So the thing is, it falls a distance d, this moves to the left a distance d, this falls down a distance d, so that's the d over here. So this is the final kinetic energy minus half M1 V1 initial square plus half M2, that's this one now, V2 final square minus half M2 V2 initial square. So that's the change in kinetic energy for number 2. For number 3, being rotational, it's half I omega final square minus half I omega initial square. So that's a change in kinetic energy for number 3. And then the delta UG1, this is going to fall down, so it's going to be plus mg delta y for 1, which is y final minus y initial, and this is going to be plus, that's m1, m2 g delta y2, that's any change in the y position of number 2, equals f dot d, these are vectors, or fd cos theta minus fd. So this would be a sort of a general equation to solve these problems. Now let's take some numbers before we plug them in, and so it becomes somewhat more easier to look at. So let's say m1 is 5 kilogram, m2 is 8 kilograms, and the coefficient of kinetic friction is 0.1, and m3, which is the mass of the pulley, we take it as 2 kilograms, rather heavy pulley. The radius of the pulley we take as 0.5 meter, so the pulley is itself a meter in diameter. If we take a smaller values, then this moment of inertia becomes extremely small, and we like to see more results. The d, the distance that it moves, is 3.0 meters. The initial speeds are all 0, so we're starting from rest, and we'll just ignore the this f. So let's just say f is 0, so we don't need to make it slightly simpler problem. And the question is, what is v final? Well, the v final for number 1 and number 2 are both going to be the same. So you can say v final 1 or v final 2. Now we plug in these numbers. So we have half, well, the v initial is 0, so this will go to 0. v2 initial will go to 0. The pulley will also not be turning. If they are not moving, the pulley is also static, so this is also 0. The delta y2 is going to be the change in the y position here, which is 0, so this is going to be 0. And we've taken this to be 0 also. So now the numbers are half, m1 is 5, and v1 final, we'll just write it as v, because there's only one velocity now, and instead of writing all subscripts, just call it a v. And instead of v1, we just write v, because v1 and v2 are the same. So this is here. This is going to be the next one from here. Half 8 v square. We come to here, plus half. Now we need the moment of inertia. So let's write, we need to have one more thing here. This pulley is in the shape of a disc. Could be in the shape of a bicycle wheel, but it's a disc. So the pulley is like a disc, okay, which means the moment of inertia is half mr square. So we'll plug that in here. This value over here becomes half, this is half m3 r square, and this is 0, plus m1g delta y, so it's going to be m1g, and the delta y is minus d, because it follows the distance d, so the final minus initial will be negative, and equals minus fd. Okay, well, before we go further, we need to get the value of f. I think we're missing something here. This was half I omega final square, there's an omega final square. Okay. So let's first find the value of f. We'll find it over here. So f is going to be mu times the normal force, and in this case the normal force is going to be simply equal to mg, because we've taken f as 0. If f were not 0, it would be something else. So the normal force is simply mg, so it's mu m2g. The value of mu we took as 0.1, m2 is 8, and g is 9.8, and this becomes 7.84. So we put 7.84 here times 3. Now we can add these two together. So half of 5th and 8th, so 8, and it becomes 13 over 2v squared. And if we look over here, well, we could do it either first find the moment of inertia and plug that in here, or we could do something else. So we'll do it this way: the half, this half, mr square, and omega is v over r. So it's going to be v square over r square. This omega becomes v over r. And the r square will cancel with this. And almost always in all these problems, you can cancel. Probably in every problem, it can be cancelled out. So that becomes the omega square. And this becomes equal, we take this on the other side, m1gd minus fd. So it's 7.84 times 3. The friction times the d. Now this is 13 by 2 v square, and this is mv square, and the m is m3, that's the pulley. So this becomes 1 by 4. The mass of the pulley is m3, that's 2. This cancels v square. m1 is 5, 9.8, and d is 3. We already took that negative. Minus 7.84 times 3 is 23.52. So this becomes 1 by 2. 13 by 2 plus 1 by 2 is 14 by 2, and 14 by 2 is 7. And these become 147 minus 23.52, or v squared becomes, subtract that, becomes 123.48 over 7, 17.64, and so the v is the square root of this number, which is 4.2 meters per second. So that becomes our speed. Okay, so that's how we solve it. And the thing you need to remember is there are two kinetic energies and a third kinetic energy, which is rotational. So two linear kinetic energies and a rotational kinetic energy. And if there's a force, then, well, the normal force will be different. And T1 is not equal to T2. Whenever there's a mass here in the pulley, T1 is not equal to T2, and you need to have them separately. So if you want to try to solve this using Newton's laws, then you would have over here T1 minus m1g and m1a, and you apply the force in the y direction, in the x direction, so you'll have a T2 here and a T1 here. They won't substitute directly. And then we'll also have to solve something over here, and we'll do this same problem in the next chapter by Newton's laws. Okay, so now the last thing we want to do is let me just do it finished off here. If an object is rolling off, so let's just do it first this way. So if you have a wheel that's turning and therefore going forward, the total kinetic energy of the wheel, because it has the center of mass has a velocity v, but it's also spinning, the total kinetic energy is going to be the kinetic energy linear plus the kinetic energy rotational. So it's going to be half mv square plus half I omega square. So it's a sum of both of them. So a wheel that's rolling down is harder to stop than if the wheel were in a little cart. Same mass, same wheel, and moving with the same velocity v as here. This would have less it would have less kinetic energy because there's only the linear part, and it's easier to stop this one. It's harder to stop this one because it has a rotational kinetic energy in addition to it. And the same thing if we look here, if we have a cylinder or a wheel that we release from rest from here, by the time it reaches here, it's moving with the velocity v. It's also spinning. So if it were not spinning, if it were in a little cart, and this mass is negligible compared to the cylinder, so we don't need to worry about that. And it also starts from v equal to 0, and it also falls from the same initial to the same final position. Then the v here, v1, v2, then v2 is going to be bigger than v1. because this has the linear kinetic energy and the rotational kinetic energy, and this has only linear kinetic energy, and this is equal to the loss of potential energy over here. So this K here is going to be equal to delta UG, and this K here is also going to be delta UG. The delta UGs are the same in this case and this case, so the K's are also the same, but this is entirely linear, and this has two components, the rotational and the linear. So a linear part which